So, welcome everyone. I think we'll go ahead and get started with our semi-plenary lecture this afternoon by Caglar, Oskay. So Caglar is a professor of civil and environmental engineering and mechanical engineering at Vanderbilt, where he directs the Multiscale Computational Mechanics Laboratory. He has received a number of awards and recognition for his research. In particular, he was named Chancellor Faculty Fellow in 2016 and ASME Fellow in 2017. And he was recently elected a Fellow of the Engineering Mechanics Institute, an organization that Caglar has been involved with quite a bit over the recent years. He received his PhD from the Civil Engineering Department at Rensselaer Polytechnic Institute, and his primary research focus is on multiscale computational modeling and simulation of material and structural systems subjected to extreme environments and loading conditions. If you ever have a chance to visit Vanderbilt and meet Caglar and his group, I really encourage you to do that. He's got a fantastic team there, excellent students working for him, and even better if you can have Caglar come and visit your own institution. He gives a fantastic talk, and I'm really looking forward to his talk this afternoon. I think it promises to be really interesting. So please join me in welcoming Caglar Oskay.
Thank you, John, for your kind introduction. And also, I would like to thank the organizers of this meeting, especially John Foster, for his kind invitation for me to give and deliver this lecture. And I will be talking today about some of our recent work on computational multiscale methods for transient dynamic simulation and understanding the dynamic behavior of architected materials. And first of all, I'd like to acknowledge two of my former PhD students, Dr. Ruizi Hu and Dr. Tong Hui, which basically have contributed significantly to what I will be talking today. And also the National Science Foundation for providing the financial support for most of this work. So what we're trying to do here is, the overarching goal for our research is to gain the ability to control the propagation of mechanical waves, the deformations and stress waves and deformation waves and so on, and how this mechanical energy is transported through solid media. And we would like to be able to control this effect through wave reflections or leveraging wave reflections, refractions, attenuations, and amplifications, all born out of the fact that we're dealing with materials that has heterogeneities embedded in them. And this is essentially possible through the advent of two important classes of materials called phononic crystals and acoustic metamaterials. And the way that we are dealing with these two materials, or we're separating these materials out, is through the manner in which they create these unique and interesting dynamic phenomenon. So phononic crystals, for example, work through wave scattering, in which the reflections and refractions at the internal material boundaries generate and basically work together to generate these unique behavior. Whereas the acoustic metamaterials work through internal resonance, where the out-of-sync oscillations, due to the significant disparity between the material constituents in terms of density, stiffness, and so on, that causes these type of internal resonance characteristics. We're particularly interested in being able to simulate large-scale structural systems subjected to transient loading conditions, and with specifically focusing on band gap phenomenon. There are very many different, very interesting things that come out of these materials and at the structural scale. But the band gap phenomenon is quite interesting, and the band gap phenomenon refers to certain frequency ranges within which the material does not admit propagation of waves. So that's what we're trying to capture. Also, another thing that we're interested in is to understand the viscoelastic properties and how those viscoelastic properties are working together with the band gap phenomenon to perhaps gain a better control of the behavior moving down the line. So there are many different types of phononic crystals and acoustic metamaterials out there. In particular, there are lattice type metamaterials that you may have seen quite a bit, especially in the mechanical metamaterials arena. And then there are also composite type metamaterials. I will be focusing more on the composite type metamaterials where we have more than one material constituent in the material microstructure. The advent of these materials are also creating some very interesting and novel engineering applications. They are very much, I'm listing just a few of them here, but they're very much in the developmental stages so far, and hasn't really made a hugely significant impact in practice, perhaps partly due to the fact that we still need additional computational methodologies to perform these analyses in a fast and efficient manner while keeping the accuracy characteristics right. So some examples here that I'm listing are the waveguiding and topological insulators. This goes to the directed energy transport, non-reciprocities and things like that are embedded in these type of applications, and also mitigation of waves of different characters, starting from impact, blast, to Rayleigh waves, for example, and even the Earth structures and so on and so forth. Of course, we're not the only ones who are doing this. There's a rich body of literature that's already going towards modeling these interesting materials, and they have various, they're attacking the problem from various different perspectives, from various different scales, starting from the characterization of the band structure through block theory, to Willis's homogenization method and gradient elasticity models. Again, these are faster approximations of the band structure characterization, towards also going towards more transient dynamic response characterization through asymptotic homogenization, computational homogenization method, all the way down to the direct numerical simulations, where this entire structural response is modeled by simply resolving everything within the structural domain, and you wouldn't believe how much that is actually employed currently in these analyses. So we will be focusing on, in this talk, particularly in the first part of the talk, asymptotic homogenization models. And then I will also introduce some addition, in view of the significant, not necessarily significant every time, but some limitations associated with homogenization. We will also try to achieve another methodology that allows us to go beyond the limitations of these homogenization approaches. So modeling wave dynamics in architected materials are affected by at least 3 different length scales. The first one is the size of the structure itself, the entire structure for which we're trying to model. The characteristic size of the unit cell. These unit cells are typically periodic when it comes to these type of materials. It may be fairly complex, but they remain to be periodic. And the length of the pertinent deformation and stress waves. If the length of this deformation wave is significantly larger than the size of the unit cell, the microstructures essentially go over basically right through the waves. This is the long wavelength regime, and classical homogenization methodologies work fairly well for these. Okay, but they also don't interact. The microstructure and the overall large structural waves do not necessarily interact very much, and they don't create these unique dynamic behavior that we're talking about. When it comes, if the wavelengths start to become of the order of the unit cell, perhaps slightly larger, perhaps slightly smaller, then we're starting to see that interaction between the wave and the material microstructure. That's where we're trying to make some contributions to. And first, again, as I mentioned, I will be looking at some non-local homogenization methods where the deformation wavelengths are slightly larger than the size of the microstructure, and then try to generalize this in a fairly recent work that I will kind of try to touch upon at the later part of my presentation, which is called Spectral Variational Multiscale Enrichment Approach. So let's start with first non-local homogenization. We're going to pose the problem in this is the classical problem for the governing equations for the dynamic response of a composite medium, the constituents of which could be elastic or viscoelastic. So the governing equations are fairly straightforward. The constitutive relation is expressed in this hereditary integral form to admit the possibility of certain type of viscoelastic properties. And you can go ahead and perform a homogenization analysis using this form, but we have found over the years that it is perhaps a bit more convenient to operate in the Laplace domain. So we take this governing equation set and we turn it into Laplace domain through Laplace transformation. And one of the good things about it is that the constitutive relation becomes very much similar to the Hooke's law. Except with the exception that, of course, the moduli tensor is complex valued, and it is a function of the Laplace number. And not only that is complex valued, actually all response fields are complex values. So that's a difficulty associated with that we have to work with complex algebra. And also in the calculations, once we perform our calculations, we need to turn them back into the time domain for assessment through inverse Laplace transform. So those are the kind of the tool sets that we're losing. And nevertheless, we will be starting our analysis with this Laplace domain the behavior or Laplace domain expression of the governing equations. Then we proceed with the classical homogenization theory, and this is the asymptotic homogenization. And there are many books written on this, so it's fairly straightforward. Perhaps one of the things that we're doing a little bit different is that the asymptotic expansions that are shown here, the asymptotic expansion of the cardinal response fields, we employ very high number of terms in those asymptotic expansions. Typically, if you have a local asymptotic expansion or local homogenization model, you include only one additional high-order term. If it's a non-local model, you include 2. We will be expanding it out all the way to 8. And then we proceed with the additive decomposition, again, a fairly standard form of the additive decomposition of the displacement field into a macroscopic contribution, the microscopic influence functions that essentially that are multiplied by the gradients of the low-order response fields, the macroscopic response fields. This is a generator function. You can basically express this to describe any order displacement field. Now, the one complication here is that the influence functions, as you go higher and higher in the asymptotic orders, those influence functions become higher and higher tensorial quantities, and the gradients that we have also become higher and higher. So that's one thing to catch, but other than that, the process is very straightforward. Then the balance equations can be expressed at several orders within the homogenization or within the asymptotic series. The influence functions that provide the effect of the material microstructure to the system can be expressed using the Macroscale balance equations, where we are solving second-order PDEs. So as you go again in this hierarchy of scales, you need the previous scale in order to be able to calculate the current scale. So we have to calculate these in a progressive fashion. But then you can also calculate the homogenized moduli. This is the concept is the generalization of the classical one, first-order homogenization, homogenized moduli, but we compute more and more of those. Then the one thing that also I would like to mention here are that these microscale problems that we are solving are all static. Even though we started from a dynamic problem, we end up with static local problems now, or microscale problems. Now, this has some benefits and some limitations. It's computationally more efficient to do this, but of course it will be providing some limitations in the applicability that I will talk about in a second. The macroscale balance equations can also be obtained through classical analysis. Of course, the reason why we're incorporating so many high-order terms is in order to capture the wave dispersion characteristics accurately. That's why we're adding these. But unfortunately for us, if you basically go through the classical homogenization derivations, that really doesn't give us anything. So at the end of the day, what happens is that every additional high-order term gives you a progressively smaller increment of additional accuracy. And in addition to that, these high-order terms also include some secular terms that cause instabilities in the system. The secularity and alleviation strategies for secularity in computational domain has actually been studied by Jacob Fish and his group back about a couple of decades ago, where they have come up with a couple of different approaches to alleviate that, such as introduction of slow time scales or tracking the mean macroscopic contribution of the response by forming a full governing equation for the full mean macroscale displacement, which we will also be adopting. But unfortunately, again, the direct combination of the macroscale balance equations to get that mean macroscale displacement doesn't capture the stop bands. So it basically gives us some reasonable dispersion characteristics, but doesn't capture the stop bands. So we have to do some additional work to bring the governing equations into a form that can capture both the stop bands and the dispersion behavior, attenuation behavior, and so on. And in the context of 1D, this is what you get at the end of the process. And I will tell you the key details in a second. But we basically have, these are the two local terms. The three terms on the right-hand side are the spatially non-local, spatially temporally non-local, and temporally non-local contributions to the system, and an asymptotic residual. That's basically the consequence of the asymptotic analysis. So the way that we are building this model is based on two key ideas. One is that we are selectively including the high-order terms through the use of a weighting parameter. And the second is that there are some very high-order gradients, as you can see up there. We don't want to deal with those, and you know why we don't want to deal with those. So we try to condense them out by expressing the high-order homogenization tensors in terms of the low-order homogenization tensors. That I will call it projection parameters, and it will make sense a little bit in a little bit. The weighting parameters are identified by simply minimizing the asymptotic residual. In the context of one-dimensional analysis, all these things are fairly standard and fairly, well, not standard, but analytically computable. And we basically can get these things very, very quickly. So what do you gain by introducing these non-local terms? Let's go back and just consider an elastic composite. In that case, we can apply the inverse Laplace transform to this problem and come up with a governing equation in the time domain if the elasticity is there for all material constituents. And you can see, first of all, that this model that we're coming up with is very similar, almost identical to the three-parameter gradient elasticity model, with the exception that all the coefficients that we have are computed directly from the material microstructure. And let's see the effect of these contributions in terms of the dispersion relationship. So here's the dispersion relationship. If you take the classical homogenization model, which is local, so there is no dispersion, you come up with a line effectively that describes the relationship between the frequency and the wave number. One approach is to add a spatially non-local term, and this is a model that has been used quite frequently in the asymptotic homogenization literature. If you put this additional non-local term, the system becomes non-local, and the behavior starts to become dispersive. But unfortunately for us, these type of models work as a low-pass filter. The waves propagate up to the stop band. Beyond the stop band, all the waves are filtered out. If you add the additional non-local terms, then you start getting a very nice, you very nicely capture the first pass band, you capture the acoustic stop band, to a certain extent to the second pass band. The one thing that I also would like to mention here, if you're looking at the optical bands and beyond basically the second pass band, the accuracy of the model degrades significantly. This is simply because of the fact that the key assumption of homogenization, which is a scale separation assumption, is no longer valid at those high frequency ranges. So there is a hard limit. So we're basically focusing on the acoustic stop band and the first pass band in our calculations right now in our analysis. Another important thing to look into is how does our accuracy change when we are changing the constituent parameters, and especially the contrast between the constituent parameters that make up our system. So here's some mixed results for that as well. So in the first pass band, we seem to be doing a fairly good job in capturing the dispersion behavior. The size of the stop band starts to become an issue as the property disparity between the material constituents become larger. Okay, this is the consequence of using static microscale problems. But so we will have to try to address this in a little bit in the second part of my presentation. The extension of this model to multidimensions are not quite straightforward, but the general scheme and the general process is the same. So we introduce weighting to describe the high-order contributions, or to introduce the high-order contributions. Now they're all, of course, tensorial quantities. And also we employ projections to take the high-order terms and express them in terms of the low-order, relatively speaking, low-order non-local terms. The question, of course, is now, how do we identify the weighting and the projection tensors? That becomes the key issue in determining how well or how accurate this model would basically be able to work. But nevertheless, the resulting system of equation is a direct extension of the one-dimensional representation that I've shown you before with 3 different non-local terms. So the next step is basically to try to understand how do we calculate the projection tensors, and let's focus on 2-dimensional models, because when you're going into these wave dynamics, there's as it gets to 3D, there's many different modes that we're exciting. In the 2D case, it's a little bit more simpler to explain. So we're going to be looking at 2 different examples. One is an anti-plane shear wave. This is a vertical shear propagating in a horizontal direction, for example, and an in-plane wave propagation where we're exciting 2 different modes: a horizontal in-plane shear wave propagation, as well as a pressure wave that is also excited at the same time, depending on the type of loading that you're applying to the system. So the projection tensors are calculated by considering specific propagation of some specific characteristic plane waves that are propagating in directions that are of high symmetry with respect to the unit cells. So if you're looking at those, we can basically then select the projection tensors so that those projection inequalities are exactly equal only when the case in the case where we're considering plane waves propagating in these high symmetry directions. We're accruing certain amount of error in other places, but we will see what the effects of that in a second. The second is the calculation of the weighting tensors. This is a generalization of what we have talked about before. We take that asymptotic residual and try to minimize that asymptotic residual so that we can obtain the best model that is possible within the context of that model form. So we rely on, again, characteristic plane waves, and we now, because we don't have analytical solutions, we form an optimization problem, a numerical optimization problem to identify these weighting tensors. And in the presence of course, some physical constraints that depend on the type of material that we're looking at. Now that we have the weighting and the projection parameters, the entire model is fully defined. Let's look at the capabilities of this. So we're looking at the anti-plane shear wave dispersion curves and there are 3 dispersion curves for this layered microstructure. This is in the direction gamma x. This one is gamma y, is parallel to the heterogeneity, and this is in the gamma m direction. All the dispersion curves, especially for the case when we're looking at the acoustic regime, seems to match very well with the block theory predictions. So we seem to be doing a fairly good job, regardless of the orientation for which this system is excited and the wave for which the wave is propagating. The same thing is true for the in-plane wave propagation. The dispersion curves seem to be accurately calculated, and in this case, as I mentioned before, there are 2 different modes that are starting. They have 2 different band gaps that are occurring at 2 different frequencies. So we're basically capturing both of them in a fairly efficient manner. The dispersion curves are great, and it's a very important tool in describing the behavior of these materials, but they're not everything. So one of the other thing that we would like to be able to capture is the transient dynamic response of structural systems subjected to or that are made by these materials. So, of course, the classical way of attacking this is you take the boundary value problem that we have formed, and we use our numerical method of choice to attack that problem directly. And that's what we did first. So, but there are some complications associated with this, solving this system. The first is that there are higher order boundary conditions that we need to pose, simply because of the fact that we have these non-local terms. The second is we need high order continuity of the displacement fields, and that can be achieved either by mixed formulations, IGA, or other methods. And worse than the last 2, which are we can deal with more or less, is the presence of some non-physical wave numbers that are in addition to the physical wave numbers that are present in this governing equation. Now that's a little bit more difficult to deal with. So here's an example of when things can go wrong. So we're basically solving the system using isogeometric analysis, and we start shaking it with an in-plane shear wave, and very quickly, before the wave starts to even time to propagate, the non-physical modes start to overwhelm the solution, and you're basically getting nonsensical results. So there are different ways of attacking this problem. The way that we have come up with is perhaps the simplest way that's possible. So we said, okay, let us come up with a reduced order representation of this model where we try to take a second order PDE, that's the general local-like description of the dynamic behavior. But let's come up with an effective moduli tensor that is non-local in and of itself. So that we will be able to, the way that we will try to do is by matching the dispersion behavior of the high order model with that of the low order model. And so since we are dealing with Laplace domain analysis, that effective moduli could be complex valued, and it is again a function of this Laplace number. And we basically match, what we do is we rely on these characteristic plane waves again, and we in that characteristic plane wave assumptions, we do analysis of the governing equations, we find the characteristic equations, we identify the physical wave numbers and the non-physical wave numbers, and we match exactly the physical wave numbers with those coming from the two second order PDE. And because of the form of the second order PDE, all the non-physical wave numbers are taken off the system. So that's essentially what we do. Then we go ahead and make sure that that system is accurate with the model order reduction. So this is these are polar plots, which basically gives us the variation of wave numbers as a function of the wave direction with respect to the unit cell for a given frequency. Note that depending on the type of microstructure you have, these are quite anisotropic behavior. And within the 80 kilohertz here refer to the onset of the first stop band, and we seem to do a great job in capturing the low frequency dynamics, the acoustic regime, very well compared to the direct numeric or the block analysis here with the reduced order model. Then we can go, and now that it's verified, we can go and start verifying the analysis of transient dynamic loading. So in this case, we're looking at a layered microstructure subjected to harmonic loading from the left end of this simple system. And we have anti-plane shear wave and in-plane shear waves that are excited with different frequencies. So let's just focus on the in-plane waves for the sake of time. The in-plane wave propagation here, if you are exciting it in relatively low frequencies, both of these waves, the shear wave and the P wave, are basically going through without much of an attenuation. If you increase the frequency to a certain extent, now you see that the SV wave is completely attenuated. We're in the first passband for the SV wave, but the P wave still is propagating. This is an important concept because in metamaterials we typically see these results where all the waves are gone. That's only true if you're exciting one mode of the wave. If there are multiple modes of the waves, some of these waves could be propagating in different frequencies. In any case, if we even further increase the frequencies to 120 kilohertz, you see that the SV waves are back alive again, and they're propagating again, whereas the P waves stop propagating in the system. Another example here is an in-plane transient harmonic wave propagation in a rectangular domain. So we have a system that's made of aluminum, and we basically place two phononic crystals at the top and the bottom of this place. And the low frequency characteristics of the base metal and the phononic crystal are the same. So the expectation is that if there's no dispersion, the behavior is more or less uniform. So, and this is subjected to different frequencies again. The movie on the lower left-hand side shows the propagation of the wave for low or long wavelength problems. If you start increasing the wave, now you're starting to see some dispersion in the phononic crystal, so the waves are slowing down. At the first stop band, the waves are completely halted in the phononic crystal, whereas the wave continues to propagate, albeit only in that region that's homogeneous and goes to the other side. So that's basically the idea of the elastic waveguide. The other question is, okay, what is the role of viscoelastic constituents? Here, the story is the same when it comes to the accuracy of the system. It seems to be doing a fairly good job in capturing the behavior, but also there is a nice interaction between the attenuation induced by material damping and the attenuation induced by this high-frequency dynamics. At 6 kilohertz, we're looking at this result here. This is a non-dispersive regime, so the attenuation of the wave that you're seeing is entirely due to the material damping. If you increase the wave frequency, now you see that the wave starts to slow down, which means that there is some dispersion, and the material damping and attenuation is working together to lower the amplitude of the wave. And finally, at 18 kilohertz, this is entirely governed by the first stop band. The wave stops traveling again. So in general, the observations that we've had for viscoelastic constituents is that you get a stronger attenuation in the entire spectrum, obviously, because of the fact that we have an additional damping mechanism. We have a stop band that occurs at relatively lower frequencies, but it reduces the stop band width as well. So those are some of the key issues associated with the viscoelastic components. Now, this works fairly well. The nonlocal homogenization approach works fairly well as long as you live within the assumptions of the homogenization theory. So if you want to go beyond that, then we have to do something a little bit different. And we have seen where those assumptions are breaking down, right? So then in the rest of the talk, I will be focusing on the definition of a spectral variational multiscale enrichment approach that we've been very recently started working on. And this, as the name indicates, that this approach is based on the variational multiscale method that was originally developed by Tom Hughes and coworkers and has been also extended in various different disciplines by many of you here. So because we are starting this work, we're going to be basically focusing on elastic constituents, and we are going to be performing analysis in the time domain. So we start by the variation of the standard variational form of the governing equation, or the bilinear form. Then we go ahead and proceed with an additive two-scale decomposition of the cardinal response field, the displacement field, into a coarse scale contribution that's defined over the entire structure, and a series of fine scale contributions that are defined over each unit cell, or a unit cell within the structure. Now, this decomposition is not asymptotic expansion, so there is no assumption of scale separation. The size of the unit cell is finite with respect to the size of the microscopic domain, or macroscopic domain, and in fact, the discretization of each element within the discretization of the macroscopic domain happens to match with a given unit cell, with a single unit cell. And if you appropriately select the function spaces, then this two-scale additive decomposition is admissible, and you can split the system into a coarse scale problem, which is solved for the coarse scale component of the displacement field, and a series of fine scale problems that are used to evaluate the fine scale problem. Now, as you can see here, the element size at the coarse scale is fixed to the unit cell. So the H refinement that's typically necessary to obtain the high frequency dynamics is no longer possible for us. So the way that we are trying to make sure that the calculations are accurate is by relying on spectral elements, or relying on elevating the element order at the core scale to make sure that we get those wave propagations right. So there's, alternative methodologies here are certainly possible, like IGA, which also admits those high order approximations in a fairly good fashion. But this is how we have proceeded in this particular work. And then you can use the classical discretization techniques to come up with the discrete system of equations, where we have a coarse scale degrees of freedom dc and a fine scale degrees of freedom df for each of the unit cells. They're coupled with each other completely. So if you want to solve this problem, you can either solve it monolithically, or you can solve it through some sort of an operator split. Unfortunately, regardless of what you do, the total number of degrees of freedom are going to be roughly equal to, maybe slightly less than, the total number of degrees of freedom of a fully resolved direct numerical simulation. So that's a major problem, of course, and the way that we're attacking this problem is coming up with a reduced order approximation of the fine scale problems. And in order to do that, we propose a material phase-based component mode synthesis approach. This is a two-step model order reduction methodology. The first step is an application of a Craig-Bampton component mode synthesis, followed by a characteristic constraint mode reduction. So the Craig-Bampton component mode synthesis is a very common approach in structural analysis of vibrational analysis of large structural systems. And the idea is very, very simple. If you have a large structural system, the vibrational response of that system can be split into the vibrational response of single system components that are stitched together by the interfacial static responses of the interfacial, because the interfaces do not have any mass, so the static responses of the interfacial relations. So we are kind of adapting this approach where the system becomes our material microstructure, and each system component becomes the phases of the material microstructure, and the interface becomes the real material interface. So the characteristic constraint mode reduction basically says that, well, you know, if you there may be significant number of degrees of freedom along the interfaces themselves, and let us try to capture those with specific mode shapes that can approximate the behavior without having to look into every single degree of freedom in the material microstructure as well. So I'm not going to go too deep into the details of this, but the idea is to take the entire system and rearrange the system in such a way that the phases are clustered together, or the contributions from each phase are clustered together. And then we perform an eigenvalue analysis and obtain the highest energy modes and truncate the rest of the modes to describe the phase behavior. The interface behavior in the classical Craig-Bampton method, you basically have to take into account every single degree of freedom along the microstructure. The second process is, again, the characteristic constraint, where we are basically taking the same idea, but now we're applying it to the interfaces, and we're taking interface mode shapes to approximate the behavior too. So that provides us with two transformation matrices, which you can apply to the fine scale system of equations to reduce their order. And the final reduced order system of equations are shown here. The degrees of freedom for the coarse scale are the same. The degrees of freedom for the fine scale are replaced by the generalized degrees of freedom for the fine scales that are much less compared to the original system. So we're going to look at two different examples. First, the first one is a phononic crystal, where the system is made up of a microstructure which has a steel core with an epoxy embedded in an epoxy matrix, again subjected to some harmonic loading. And we are applying 4 different frequencies here and looking at the comparison between the direct numerical simulations and our approach with respect to the velocity profiles. And as you can see, they're fairly close to each other. And one of the things I would like to mention here, is that the frequencies at which we're exciting this system is way beyond the capabilities of the homogenization theory. Actually, if you look at the lower right-hand side plot, where the blue lines is within the second of the optical stop band of the system. So we can basically go all the way up to the second optical stop band and so on. The second example that I'm going to show is a similar idea, but now we have an acoustic metamaterial instead of a phononic crystal. So the only difference here in this example is that you have a microstructure that has a lead core coated with rubber embedded in an epoxy matrix. And we're applying the same thing. We're applying a harmonic loading from the left-hand side of the structure. And there are two things that are clear here. The one thing is that the applied frequencies that you're seeing here is in the order of 500 to 2700 hertz. This is at least an order of magnitude smaller than the ones that we have to excite for the phononic crystals. Now the band gap has shifted an order of magnitude. The second is that the profiles here, the deformation profiles, is very, very different.
in the same passband or in the same stop band is very, very different compared to a phononic crystal. That points to the fact that they are operating in very different mechanisms, even though they are applying or obtaining the same wave attenuation behavior, they are operating in very different mechanisms. So another thing that we have ensured was the accuracy of the behavior with respect to the number of mode shapes that we employed in the reduced order model. And as you can see, we cannot do this with just a couple of modes. You need to have substantial amount of modes. Approximately 160 to 320 were used for the acoustic metamaterial example. The phononic crystals are a little bit better, but acoustic metamaterials require significant amount of modes. And a question that comes to mind right away is, why do we do this model order reduction? Why don't we just simply take the unit cell, do eigenvalue analysis of the unit cell, and apply those modes instead of this, this two-step approach? Then the point is that approach, even if you use very large number of modes, doesn't work. This because of the fact that the contrast between the properties of the materials are very, very high, especially for acoustic metamaterials. So, and the computational efficiency of this approach is at least an order of magnitude faster than the direct numerical simulations, which is one of the key issues that we wanted to address. So the final example that I have is another elastic waveguide, but this one is a little bit more complicated, where you have a phononic crystal with the exception of a path that looks like an S shape. And again, we're going to excite the system from the left-hand side with an harmonic loading with different frequencies, with two different frequencies, okay? And I would like you to focus especially in the first stop band where the wave is entirely, the wave is basically applied from the entire domain, or the entire left-hand side of the domain. And the wave starts to essentially travel because we are in this first stop band of the phononic crystal. It travels, it hits the phononic band, goes up, turns again, and goes to the other side of the domain. And this is only it's basically the wave we are achieving wave propagation perpendicular to the excitation. That's essentially what it's doing. And this is also qualitatively speaking, matches very well with the experimental observations as well. And with that, I would like to conclude my talk. So we have basically talked about two different methodologies that allows us to perform simulations with these interesting classes of materials. The first one is a non-local homogenization. As I mentioned, this is a great, method or tool set that would allow you to perform simulations provided that you're within the bands or within the bandwidth of the homogenization theory. It is possible, especially in the acoustic metamaterial world, it is possible to hit the boundaries or the capabilities of the homogenization pretty quickly. Now, the variational multiscale based approach works for much larger ranges of materials, but of course, as you can clearly see, there are significant issues that needs to be addressed there to make the applicability of this system more generic. But either way, we are significantly improving the computational cost with respect to other methodologies, especially direct numerical simulations for transient dynamic analysis, and that hopefully will allow us to employ these type of methodologies for design. But we're not talking about just microstructure design that can be done with classical block theories or structural design for a given microstructure, but the design where the microstructure and the structure itself can be designed together. So that's perhaps one of the areas that we wish to go in the near future. And with that, I would like to thank you all, and this is all I have to say. Thank you.